Good day and welcome to our talk on AI-based robust convex relaxations for supporting diverse QoS and next-generation wireless systems, such as 5G, beyond 5G, and 6G systems. My name is Steve Chan, and I'll be presenting on behalf of myself and my co-authors Marwan, Krunz, and Bob Griffin. The table of contents and the structure of the talk today will be in 5 sections: introduction, background, numerical challenges, such as numerical instability, and solutions, such as our positive robust convex relaxation or RCR architecture, experimentation findings, and finally, concluding remarks. For Section 1, the introduction, we will cover some mission-critical quality of service QoS applications as well as some QoS technical challenges. Some examples of mission-critical quality of service applications include connected autonomous vehicles, ranging from driverless cars to drones, augmented virtual reality, ranging from surgical training to engineering, industrial Internet of Things, ranging from industrial control systems to communication systems. And some examples of QoS technical challenges include non-convex optimization problems, which have multiple local optima, and we may never reach a global optimum. And along the vein of optimization problems, mixed integer programming or MIP problems are encountered in the 5G, beyond 5G, and 6G ecosystem, such as mixed integer nonlinear programming MINLP problems. For Section 2, the background, we will cover shaping the problem space, in other words, our goal of having convex problems to solve rather than non-convex problems to solve, approaching the problem space, in other words, our evaluation of various stochastic search approaches, and describing the MIP pathways to reach the desired convex problem paradigm. Slide 6 shows a nonlinear, continuous-discontinuous MIP ecosystem. Slide 7 shows a nonlinear, discrete ecosystem. Slide 8 shows them jointly. We then place where the set of mixed integer nonlinear programming, MINLP problems, reside, and we also place yellow arrows to indicate where we began at MIP and ended with MINLP. Some of the stochastic search approaches to reach our goal of convex optimizations include genetic differential evolution, colony optimization, and particle swarm optimization. There are some distinct deficiencies with the first 3 approaches. For example, if the initial swarm size is too small, the algorithm will gravitate to a local minimum and not reach a globally optimal solution. If the initial swarm size is too large, the computational overhead increases. The 4th approach does not have the described deficiencies, and among other advantages of PSO, regardless of the initial swarm size chosen, the solutions are generally good enough in relatively few iterations. And with PSO, it is possible to prove the optimality of the solution. To illustrate how we reach the desired convex problem paradigm, we will describe the relevant MIP pathways. To start, Slide 11 shows a linear, continuous-discontinuous MIP ecosystem. Slide 12 shows a linear, discrete ecosystem. Slide 13 shows them jointly. We then place where the set of mixed integer linear programming, MILP problems, reside, and we also place yellow arrows to indicate where we began at MIP and ended with MILP. We then note where the set of MINLP problems reside and where the set of MILP problems reside. We then place yellow arrows to indicate where we can begin at MINLP and end with MILP through a sequence of transformations for linearization. Next, we combine what was previously presented in slides 6 through 15, everything into one chart, and observe the various pathways to attain a convex problem paradigm. For the convex problem paradigm, we focus on convex relaxations. Simplistic implementations are not robust enough and do not provide sufficient insight as to what is happening at each neural network layer. Our approach utilizes convex surrogates, wherein convex relaxations are optimally fitted to a series of convex approximations applied to the involved non-convex problems. These robust convex relaxations, or RCR, are employed at each neural network layer, and the collective series of these RCRs are nicely suited for PSO. The specific implementation of PSO is shown in Slide 19. In essence, for the reduced number of hyperparameters to tune, each constitutes a near-optimal convex optimization. The challenge of PSO is that the required conversion of continuous-discontinuous hyperparameters to discrete values can lead to premature stagnation of the PSO particles at local optima, which can prevent reaching the global optimum. The premature stagnation issue is further shown in Slide 21, and our solution towards contending with the issue is to increase the inertia of the PSO particles via an adaptive inertial weighting system atop a modified GNU octave system. A complication of this approach is that increasing the inertial weighting may spawn further non-convex problems. And the pathway is shown in Slide 23, which starts at MIP, progresses to MINLP, and ends at the non-convex problem paradigm. In addressing these issues, we uncovered some numerical stability challenges of some of the required functions, and this segues to Section 3, Numerical Challenges. This section describes some dependencies whereby we had to either wait the technical fixes from the creators of the Involved Function Library Toolkit framework, or we could proceed to undertake modifying some of these functions atop our own forked modified platform. In this case, we utilized the reference modified GNU octave platform. Some of these issues are shown in Slide 25. For Section 4, Experimentation, we progress to the selection of the machine learning libraries toolkits, as well as the selection of the underpinnings for our convolutional neural network, such as a specific version of You Only Look Once, YOLO, which was best suited for our approach. We explored the various machine learning libraries toolkits with a focus on the core functions for 5G, BFG, and 6G. We settled upon PyTorch, which encompassed about half of the involved functions, as can be seen in slide 27. We also added in Caffe and Caffe2, as all three are quote-unquote interoperable via the Open Neural Network Exchange ONNX format. As can be seen in slide 30, TensorFlow would have been another option, followed by SciPy and Julia. Accordingly, we selected the PyTorch implementation of YOLO v3. As such, our DCGAN was renamed DC YOLO v3 GAN. As we also used squeezed convolutional layers to replace certain convolutional layers, DC YOLO v3 GAN became a modified squeezed DC YOLO v3 GAN instantiation, or MSY3I. We found that PyTorch version 0.4.1 was quite stable with regards to the involved functions. Hence, we utilized it for our key solver for the convex optimization problems, named MSY3I number 1. Ironically, even though PyTorch version 1.7.0 was a higher version number, it was less numerically stable for the involved functions. However, as the overall performance was better, we utilized it for our key solver for the modified involved functions. To stabilize the PyTorch version 1.7.0 based key solver for the modified involved functions, named MSY3I number 2, we utilized a TensorFlow version 2.0 based mitigator against most failure collapse, named DCGAN number 3. The key solver for convex optimization problems, which includes PyTorch version 0.4.1 based MSY3I number 1, is referred to as RCR paradigm number 1. The key solver for the modified involved functions, which includes a PyTorch version 1.7.0 based MSY3I number 2, is referred to as RCR paradigm number 2. The details of each RCR paradigm is shown on slide 36. Overall, the two RCR paradigms and the mitigator are referred to as our RCR architecture. In conclusion, our paper presented an RCR architecture which could not only resolve the task 5G QoS related convex optimization problems, but could also leverage the same RCR mechanisms for tuning its own hyperparameters. The RCR architectural stack achieved this via three distinct phases: effectuating an RCR paradigm via bespoke MSY3I, using a PSO to tune to MSY3I so as to reduce the associated computational costs, and operationalizing the PSO via an adaptive inertial weighting mechanism facilitated by the modified GNU octave system. Overall, the RCR architecture presented in our paper demonstrates promise. Thank you very much for listening to our talk, and have a great conference.